Technology, Goa, and belongs to Department of Mechanical Engineering. He is formerly scientist at A Star at National Institute of National University of Singapore. A-STAR stands for Scientific Agency for Science, Technology and Research, Singapore. And prior to that, he was a research scientist at School of Computer Science and Engineering, Nanyang Technical University, Singapore. Prior to that, he did his postdoctoral research at NTU, Singapore. He did his PhD from Engineering Science, University of Auckland, New Zealand, and before to that he did his BTech degree from National Institute of Technology, Rourkela. Dr. Abhishek is the founding researcher of this transfer learning based multitask optimization technique, and his papers are highly cited throughout the world. He was the recipient of 2023 and 2021, uh, 2023 and 2019 IEEE Transaction on Evolutionary Competition Outstanding Paper Award. He is an associate editor of IEEE Transaction on Evolutionary Competition, and his research articles have received near about 7,000 research citation in the Google Scholar with H index 42 and I10 index 76. Personally, I have attended first time his lecture in IEEE Congress in Evolutionary Competition 2019, where he has taken a special session on demonstrating the multifactorial evolutionary competition. And I was very impressed with the way he has represented in that particular talk. And today I am fortunate enough, along with all participants, to listen to him again. So I welcome you, Dr. Abhishek, to this faculty development program on advanced optimization technique using MATLAB.
Thank you so much
Over,
for that.
over to you, Dr. Abhishek.
Thank you so much, Dr. Nanda, for that fantastic introduction. Okay, so thank you everyone for attending. I understand a very good afternoon. I suppose most of you are attending from India, so it's afternoon for us. Okay, so with that, let me jump to the talk. As Dr. Nanda was saying, I'm a Ramanujan faculty fellow at IIT Goa at the moment. Before this, I was a scientist at Singapore, multiple institutions, A-STAR, which is the Agency for Science, Technology and Research, and NTU, Nanyang Technological University. The reason I mention this is because a lot of the beginnings of the work that I'm going to talk about today come from my time spent in Singapore. So it's extremely important for me to acknowledge that affiliation clearly. I have stated my email address here as well. So in case after the talk we do not have sufficient time for Q&A, please feel free to get in touch with me offline anytime. Drop me a message and I'm certain to get back to you with an answer. Okay, so the topic of my talk today is transfer and multitask optimization of black box functions. Before we get into the technical details of what is transfer and multitasking in the optimization context, let me start with a few motivating observations. So if you look at a lot of scientific and engineering optimization problems out there, one thing you notice is they do not have analytical expressions for the objective and constraint functions that you're trying to deal with. So in other words, the functions are black boxes. You either have to run a computer experiment, a computer simulation, or you have to go out in the laboratory and do a physical experimentation to calculate what is the performance of a particular candidate solution. Right. As a result, a lot of these function evaluations are quite expensive. Running a computer simulation could take time, and of course, running a physical experimentation could consume both time and monetary cost, right? So as a result, we have a high cost of data acquisition in these problems. And as a result, further result, when you're optimizing, there is task-specific data scarcity. So on one hand, you do not have a mathematical expression for the objectives you're optimizing. And on the other hand, you cannot even sample a lot of data corresponding to those objectives because that data is expensive to get. Now, just to make this point a little more concrete, I'll take a few examples from problems that I have myself worked on in the past. So we'll start with this example in air breathing engines. So these are aircraft engines. This is a problem I worked on during my time at Rolls-Royce corporate lab in NTU. So here, when you're running a single aircraft engine simulation to compute whatever performance metrics you're interested in, one simulation for one engine design can take several days, in particular in the order of 10 to 15 days for one simulation. So that's one function evaluation. Here is a problem from optimizing composite materials manufacturing processes. So this is the one, this is a problem I looked at during my PhD. So here doing one computer simulation to evaluate process parameters, the performance of process parameters takes several hours. So again, one function evaluation to get what the objective function is corresponding to one candidate solution, it's going to take you several hours. Here is another example in biomedical micro device design. In this case, we have a crude simulation, multi-physics simulation that we've created. But in actuality, what you want to do is actually you want to fabricate a part. So given a particular design of a magnetic sifter is a separator. It separates different cell types from a mixture. So we'll get into this example more later on when I talk about real world examples. But the thing to note is here you'll actually want to fabricate the part and then run a physical experimentation to actually compute what the performance metrics are. We do have a multi-physics simulation for this, a very crude multi-physics simulation, which allows you to come up with approximate performance scores. But in reality, you want to actually fabricate this, run an experiment, and calculate the performance metrics. So again, this is a very, very costly affair. Just running one simulation to get one data point can consume a lot of time and resources. So given all of this, one thing we notice is that a lot of conventional optimization algorithms out there, black box algorithms out there, when I say black box, I'm talking about those algorithms which do not explicitly require the definition of a mathematical objective function or constraint. So they can just work with queries. So based on queries, they can sample candidate solutions, evaluate them, and then update the search accordingly. So algorithms of that kind, and you have evolutionary algorithms following into this category. If you look at these algorithms, most of them are population based, and as a result, it's simply unaffordable to solve problems of this kind. Because in a population based method, you are sampling and evaluating hundreds of solutions over multiple iterations. And when the cost of one solution is so expensive, it takes days or hours or several dollars. Evaluating a population and then updating it from one generation to the next is simply unaffordable. Okay. So when we're talking about these kinds of problems, here's an interesting question that motivates the entire transfer and multitask optimization paradigm. It's that can we discover high quality solutions quickly and at low cost? So quickly in terms of time and at low cost in terms of dollars, for example, by making use of informative priors from related tasks. So since there is task specific data scarcity, so within the context of a particular task, the data is very expensive. Can I make use of data from other related tasks, which I might have acquired beforehand, and use that to optimize the current new task more efficiently? Okay, so these informative priors could either be just data that I've acquired from previous problems, or they could even be different kinds of models like surrogate models and so on, which I've acquired from previous problems that I've solved. So this is the question that lies at the heart of what we are trying to do in transfer optimization or multitask optimization. Can we use these informative priors from related tasks to help optimize new tasks which are efficient, which are expensive, more efficiently? Okay. Uh, can I be heard? Am I clear?
Yes, Dr. Abhishek, you are clear.
Okay.
Perfect going on.
Okay. So here's a definition, a very simplistic definition of transfer optimization that we put forward a few years ago in a TTCI paper. This is Transactions in Emerging Topics of Computational Intelligence. We said that given a set of source tasks, TS1, TS2, so on, so there are K source tasks, and a target task T sub T, transfer optimization aims to enhance the convergence rate of your target optimization procedure by transferring and reusing data and or learned models. So these are the informative priors I was talking about, acquired from various sources. So various sources, all the different K source tasks that you've solved in the past. So here's a picture that makes this hopefully a little more illustrative. So let's imagine that over time I've solved different source optimization problems, K source optimization problems in particular, and corresponding to all of them, I've stored some data. So it could be either raw data of candidate solutions and their evaluation scores, or these databases could also contain surrogate models and so on. Now, given a new target problem instance, this is T sub T, and its corresponding optimization loop. So this is a standard, black box optimization loop where I'm sampling solutions, evaluating them, and then updating so on. So given this iterative loop, is it possible for me to somehow transform and make use of all of this data that I have acquired before, transform it somehow, and use it in to inform this optimization loop of my current problem instance? Okay, so this could be done in various ways, but of course there are certain fundamental questions that we need to address when we are talking about this issue. The first is how to be sure that the transfer that we are doing from the various sources to the target is useful, or at least it's not harmful. Okay, what do we mean by harmful? It means that by doing transfer, you were better off not doing transfer in the first place. So that's the whole point. So if you were better off not doing transfer in the first place, then the transfer was harmful for you. Okay. So if we under this essential idea, there are several questions that we've identified, and those are as follows. So how to select what to transfer, especially when you have multiple sources. In the previous slide, we were saying that suppose you solved K optimization problems before. Some of them may be more related to the target than the others. Some of them may be unrelated to the target, and so on. Okay. So if I transfer information from an unrelated source to the target, so I transfer models or data from an unrelated source to the target, then I might have negative transfer, which in other words means that I was better off not transferring at all. Okay. So I don't want that. I don't want to transfer from sources which are not relevant. But beforehand, I do not know which sources are relevant, which sources are not so relevant. So that's one thing. I need to select which sources to transfer from. Furthermore, I need to determine how much to transfer. This is sort of like deciding the weightage. How much weightage am I giving to different sources? Okay. If I transfer excessive amounts of data from insufficiently correlated sources, then I can have negative effects again, right? On the other hand, if I transfer insufficiently from a highly correlated source, then that's like a missed opportunity. I had a lot of relevant data from a relevant source task, but I was not able to use it, right? So that's a missed opportunity. So I need to be able to decide and weight how much I want to transfer from the various sources. So not only do I need to select either I transfer or not, but I also need to weight it. How much do I transfer from a particular source? I don't want to overdo it from an partially related source, and I don't want to transfer insufficiently from a highly related source. I want to make use of a highly related source as much as possible. Again, so that's a key question that our algorithm needs to figure out. Furthermore, how to define domain adaptations in cases of source target heterogeneity. So what does that mean? Uh, Source target heterogeneity in transfer optimization, we define as scenarios where the solution space of the source and the target task differ. So the design variables or the decision variables are not exactly the same in the source and the target task. Okay. They may be overlapping. So some of the design variables are common, but there could be certain design variables which are task specific. Okay. So there is no perfect overlap between the design or decision spaces of the source and target tasks. So if you have a scenario like this where the design spaces or the search spaces are not perfectly overlapping, it is not immediately obvious how to do transfer. When we talk about the methods, it will hopefully become clear that in a scenario where the search spaces don't perfectly overlap, how to do transfer is not clear. So you need to figure out some way to take heterogeneous spaces, okay, non-identical spaces, or spaces with non-identical features, and adapt them, okay, in some way such that after adaptation I can do the transfer. So I need to learn this kind of unified space in which I can do transfer. If there isn't any unified space, then it's not obvious how to do it. Okay. Now, in the subsequent slides, we hope to address some of these questions. Of course, they are not comprehensively solved by any means. What I'll talk about is certain kinds of algorithms that my group and I have been working on for the last few years. Of course, it's not comprehensive. Which these questions context of probability. Okay, so now let's move on to, with that introduction, let's move on to approaches and methods. I'm particularly going to talk about this probabilistic view of population-based search, evolutionary algorithms, in other words. Uh, and what I'm going to show in this slide, if you, any of you are really interested in the theoretical, you know, a fundamental theoretical explanation of a lot of modern evolutionary algorithms, I strongly encourage you to read this paper on information geometric optimization, published in 2017 in GMLR. So that's the Journal of Machine Learning Research. Anybody interested in the theory, the underlying theory of IGO, that's information geometric optimization, and how it explains, how it gives a unifying basis to a lot of different evolutionary algorithms out there, including things like CMAES, natural evolution strategies, and so on, estimation of distribution algorithms, probabilistic type EAs. This is really a modern classic. This paper really is an excellent resource on understanding this unifying theoretical basis of many of these probabilistic evolutionary algorithms. I'm not going to go into this in detail, but I'm going to give you a flavor of what this is about, and then we'll move on to how this can be adapted to our transfer settings. So consider in a typical setup, there is some objective function f of x that I'm trying to maximize. And I have a search space x here, and I'm looking for solutions in this space that maximize my f of x. For simplicity, in this slide, I have ignored constraints. Okay, so this is an unconstrained problem, and we want to maximize f of x. In the probabilistic setting, this particular problem is transformed as follows. Instead of looking for raw solutions x in the search space, what we are now looking for is a probability distribution, p of x. And we are maximizing the expectation of your objective function value over this probability distribution. Okay. Now, what this probability distribution represents is the underlying distribution of a population in an evolutionary algorithm. Okay. And what I'm trying to do is find a distribution such that the expectation of my objective function over that distribution is maximized. Now, if you look at a lot of algorithms in the IGO family that solve this formulation on the right-hand side, it doesn't, so it works with probabilistic, often, not always, but often works with probabilistic models where all we need to do is be able to sample the models. So we don't need to explicitly define the probability densities corresponding to a particular solution, as long as I'm able to sample the model. Okay. So as a result, you'll see that there are many different variants of these probabilistic based algorithms that incorporate a lot of modern generative AI techniques. So this P of X can either, in the simplest case, be a Gaussian, which is what you have in algorithms like the CMAES, which is a classic, or the XNES, and so on. So those are standard algorithms that we use all the time, where P of X is in the form of a simple Gaussian. Or on the other hand, you could have P of X in the form of a GANs, or it could be a variational autoencoder. So for instance, I have cited a paper here which uses a denoising autoencoder to do the sampling. Okay. So again, this sampling is essentially a sampling of your candidate population in an evolutionary algorithm. So all I need to do is I need to have a generative model that allows me to sample. Once I do that, I can design an algorithm around it. I don't necessarily always need to explicitly know what the probability density is corresponding to a particular X. So there are many algorithms that can be formulated based on this mathematical framework on the right hand side, which incorporates a lot of modern Gen AI type techniques. Okay, so now why does this work? So if you look at it, suppose I was solving the problem on the left hand side here, and suppose the optimum is X star. Okay, so X star is my global optimum that maximizes my objective function f of x. Then, if X star is the optimum of the left hand side, then you can prove, and there's a proof here in that came out many years ago, 2004, on a particular class of probabilistic model based methods, that if the solution of the left hand side is X star, then the solution of the right hand side under certain conditions will converge to a Dirac delta function. So this delta represents a Dirac delta function. So essentially you can think of it as a Gaussian with zero variance. Okay, so it's a degenerate Gaussian which is collapsed onto X star. So it's the probability density is non-zero at X star and zero everywhere else. That's what the Dirac delta function is. So if the solution of the left-hand side is X star, then the solution of the right-hand side under certain conditions asymptotically will converge to a Dirac delta function centered at X star. Okay. So in other words, if I get, and how do we get this? This essentially follows from the translational property of Dirac delta functions. So anybody interested in how this convergence comes about, I strongly encourage you, and under what conditions they prove this, I strongly encourage you to have a look at this paper. But the essential idea is once it converges, and once I can get the Dirac delta function corresponding to the problem on the right hand side, I can immediately extract what the solution of the left hand side is. Okay. So once I get the Dirac delta function on the right, I can get X star on the left. So essentially, I've solved the same problem, but using a different approach. Now, of course, in reality, you never really wait for your P of X to converge onto the Dirac delta function. You don't wait for perfect convergence. You usually will terminate your search once you have a reasonably satisfactory solution and your search is stabilizing. So you're not improving much over multiple iterations. So typically, because these proofs of convergence are asymptotic proofs of convergence. So they say that at t tends to infinity, your search algorithm will converge. But of course, in practice, we are not going to go to, we are not going to solve the problem forever. So we'll just stop at some meaningful time when the solutions we have are satisfactory. And let's assume that when we stop our search, so we have some, we have found a solution which is good enough and it's stable, so it's not changing very drastically given more iterations. Let's say the probabilistic model at that time is P star X. Okay, so it's not a Dirac delta function, but it's a probabilistic model that is more or less converged around your optimum. Okay, so it hasn't degenerated to a Dirac, but it sort of gives you a representation of where the good solutions lie. Now, what we can do is once we solve this problem, this can correspond to any f of x, I can store the corresponding p star x. So this is a piece of knowledge that I have acquired from solving my f of x. So p star x gives me the distribution of solutions which are good for f of x. Okay. So this is a piece of knowledge I acquired by solving a task, which I can then store for future transfer and reuse. Now, how do you transfer and reuse? That's the subsequent question. So we'll continue with our probabilistic modeling formulation. So if you see, let's look at case one, which is source target homogeneity. So this means that the search spaces of the source and target tasks are common. This is different from the heterogeneous case that I was talking about earlier, where the source and target task input features or design variables may differ. So let's consider the simpler case where the source and target search spaces are common, but their objective functions can differ, of course. Okay. So this is the, so on the left-hand side, what we have now is the probabilistic formulation of your target optimization problem. So P sub T represents a probability distribution corresponding to your target task. So you want to find P sub Tx. In the transfer setting now, we reformulate this particular formulation as follows. Okay. So this can be a little daunting, but let me take you through this. Essentially, what we are doing is we are replacing this singular probabilistic model which you had for just the target task with this probability mixture model. And this probability mixture model now includes all the information you have acquired from previous problems that you solved. So like I said in the previous slide, each time I solve a problem, I can extract a P star X. So this is the distribution of good solutions corresponding to that previous task. So I have all of these models, probability distributions from all the previous tasks I've solved. And based on that, I can now define this mixture model. And this mixture model has weights, of course. So I'm searching for these weights. These are also now my parameters that I want to optimize, as well as the PT. Notice that P star S is already known. It's known from a previous problem, so I don't have to optimize that. I do have to optimize PTX, P sub TX, and I have to optimize my parameters. Okay. Now, these parameters allow you to decide in a very natural way what is the weightage you want to give to a particular source task. So if a source task is highly relevant, then you want the corresponding W's to be large. Okay. Remember, what is this probabilistic model doing? This probabilistic model is the underlying probability distribution of your population. So I am sampling my candidate solutions from this mixture model. If a particular coefficient is large, that means that I am sampling a lot of solutions corresponding to that source, corresponding to the probabilistic model from that source. So if a particular source task is indeed highly related to my target task, I want to sample a lot of candidate solutions from that probabilistic model. And this formulation encapsulates this whole idea very neatly. Okay. So through this, and of course, if there is a particular source which is not related to the target, which I do not want to sample, then the corresponding weight should simply be 0. As you see here, all these weights are greater than or equal to 0, and they should sum to 1, which is standard requirement for a mixture model. So if there is an unrelated source, I simply want this to be 0. If it is a highly related source, I want the W's to be high. Okay. So this whole thing encapsulates this idea of transferring how much and selection very nicely in one formulation. Now, the thing to note here, as I was saying in the previous slide, that this P star X could be any probabilistic model. So it could either be a Gaussian in the simplest case, like in a CMAES, or it could be a GAN or a variational autoencoder. But you can take that further. You could have these priors, these probabilistic models, informative priors, coming from an LLM. So you could actually appropriately prompt an LLM with, for example, a description of your target task and some sample evaluation data, some small amount of evaluation data, using this idea of in-context learning. So you can provide this as a prompt to your LLM and ask your LLM solutions for you or to propose solutions for you. So remember, all we need to do in most algorithms that implement this right-hand side is to be able to sample the probability distribution. So sample P star X and sample PTX. That sampling can be done by an LLM. I can give a description of a task to an LLM and ask it to propose solutions. Okay. So this is a fantastic emerging area. There is one paper, at least that I know of, that came out last year in iClear, that starts looking at this idea, how to use large language models as informative priors. So priors from, LLMs are trained on essentially the entire internet. So there's a good chance that the LLM knows something about the optimization problem that you're trying to solve. It may not know everything explicitly, exactly, but it might have an idea. So it has that prior knowledge. Are we able to leverage it for our optimization purposes? This was a paper in iClear 2024 that shows that it could be possible in a Bayesian optimization setting. So Bayesian optimization is, again, another probabilistic model-based approach, which is not very different from what we are talking about today. So this is a fascinating direction. How do you use these priors in this kind of mixture model formulation to inform your target search optimization? Now, how to work in case 2, I'm not going to go too much in depth of this. So in case 2, you're talking about source target heterogeneity. So your XT and XS are not the same. So your search space of the target and search space of the source may differ. So if this is the case, then you have to try to learn a mapping. So this M represents a mapping from XS to XT. And these probabilistic models, these source probabilistic models that you have from your from your source task also need to be appropriately transformed through MS, through this mapping function that you learn. Okay, so PM, so you notice here there is no M. The probabilistic models are just used directly because the search space was common. Here we have a P star MS, and that's because the probabilistic model is now transformed through M, this mapping function that you learn. So this is an additional learning step that you need to do if you have source target heterogeneity. The features are not the same. And I'm not going to go into the details of this. Anybody interested in this, there is a quite a lengthy paper on this that we have in Cognitive Computation Journal, which talks about this M mapping function taking a nonlinear form and how you can, in particular, in neural nets. So M is a neural net that maps a point in the source domain to the target domain. Okay, so anybody interested can look at this paper. All right. Now we come to multitask. So multitask in spirit is very similar in the most part to what transfer optimization is about. The only difference is that the tasks are not, or I shouldn't say the only difference, but one of the differences which are probably most talked about is that the different tasks are not separated in time. So in multitask optimization, all the tasks occur at the same time, or you're assuming to solve them at the same time, and they are not separated. So you don't have priors that you've drawn from problems solved previously. So it's all the tasks being optimized simultaneously, and they can share information, talk to each other. So that's essentially the idea, and that is reflected in the mathematical formulation here. So essentially, it's the same thing. So you are maximizing the expectation of your objective function over this probability mixture model, but you're summing this over all the tasks that you have. So let's assume we have k tasks and we want to solve them simultaneously. Then we simply sum this expectation of the objective function over the mixture model, and there's a separate mixture model for each task. And each mixture model looks at probabilistic models drawn from all the other tasks that are there in your set. So I'm dealing with a set of k tasks, and this mixture models combines all the probabilistic models from all of them. Okay. So again, in spirit, it's very similar to transfer, but of course, multitasking gives rise to certain very interesting properties which are beyond just speed up. But I guess today, given limited time, I'm not going to touch on that. So anybody who's interested in going into really the depths of how this particular formulation can be addressed, can be solved, I invite you to look at all of our papers in this field. So the original paper, as Dr. Nanda was saying, was the 2016 multifactorial evolution paper, uh, which is what got the 2019 IEEE Transactions Outstanding Paper Award. That one did not have this precise mathematical formulation. So the 2016 paper, we just introduced the idea of what a multifactorial evolution algorithm might be, this idea of multitasking, without going into the mathematical details. But then in 2020, we published a second version. So we called it MFEA 2, where we actually went in and did all the theoretical analysis and showed that the MFEA algorithm actually contains this hidden probabilistic structure, that this hidden mixture model exists in the MFEA, and accordingly, you can solve this particular formulation with certain adaptations. So there are adaptations which allow you to essentially adapt W's, these weightings. As if you remember from the last slide, these weightings tell you how much you want to transfer from a given source or from another task. So MFEA 2 allows you to adapt that, whereas in MFEA 1, these W's were fixed. Okay. So again, anybody interested in just the introductory basics of multitasking or the deeper theoretical side of multitasking, I strongly encourage you to have a look at these two papers. Then there's another 2022 paper which goes into real world applications of this idea. Okay. Now, how exactly do you learn the mixture coefficients? We've spoken about the mixture coefficients so far. These are the W's, which tell you how much to transfer and so on. But we need an algorithm to learn those W's so that they behave the way we want it to. Okay. So there are several, again, techniques that we put forward in the literature. This is the first one published in 2018. So this is a very simple idea. At any transfer iteration, so in an evolutionary algorithm, imagine that I am transferring every few iterations. Then let at a given iteration my target population be x1, x2, xn, so on. What I want to do is find a probability mixture model. So this is the mixture models that we've been talking about that maximizes the likelihood of your target population. So I want to learn my W1, W2, and so on, as well as my PT that maximizes the probability, the likelihood of observing my target population. Now, the idea, the theory of this follows directly from estimation of distribution algorithms and the convergence proofs of estimation of distribution algorithms. So I won't go into that, but this is a very simple idea. Anybody interested in the theory can go ahead and have a look at the paper or the convergence results for EDAs. So solving this particular optimization problem now, so this is an embedded optimization problem within your target optimization. So to solve this, we proposed a two-step method. We first built a model of PTX. So this is just an intermediate target probabilistic model. So this we added some corruption to this target population data, corrupted it a bit, and then built a probabilistic model for that corrupted data set instead of the original data set, just so that it doesn't overfit. So that was the first step. And secondly, once you've built PT, the W's can be learned using the stack density estimation algorithm. So you can show that given a PT, this remaining algorithm, this remaining loss function is essentially convex. So there are many algorithms out there that can find the W's for you. The stack density estimation is one of them, which was proposed in EURIPS 97. So we've used this algorithm. So once you do this, you can essentially find all the W's and the PT at any given iteration of your transfer evolutionary algorithm. But what is the challenge of this? So this was in 2018, as you see, so it's been quite a few years. This step two, where you optimize the mixture coefficients, this can become expensive if K is large. Okay, so you need to construct this. You need to calculate these probability densities corresponding to all K sources. Say K is the number of sources you have. So corresponding to all the sources, you have to calculate the probability densities, which can take a lot of time. So this whole algorithm is slow. And secondly, stack density estimation, this algorithm requires you to explicitly measure probability densities. So you need to be able to define this P star SXN, this quantity and this quantity, the probability densities have to be defined. And if that is the case, then it's not enough to just have a generative model that you can sample. You need a generative model that allows you to measure what explicitly what the probability densities are. So as a result, this particular method that we had in 2018 is unfortunately not compatible with modern generative algorithms or LLMs for that matter. Okay, so to address this issue, we came up with another approach in 2023. This is what we call the scalable transfer evolutionary optimization algorithm. Uh, it's very similar in flavor. So essentially, this is the mixture model we are trying to learn in this paper. Also, it's the same mixture model, but instead of trying to learn the W's optimally in every iteration, we try to co-evolve the target population and the W's at the same time. So instead of running a full stack density estimation algorithm to find the optimum W's, we co-evolve the target population. So that's represented by PTX, as well as the W1, W2, WK, and so on. Okay, so all the weights. So there are two separate populations, one evolving a target population, one evolving the W's, and these co-evolve simultaneously. And this co-evolution of the W's in particular is done by just a 1+1 ES. Okay, so since we are compromising on the optimal W's, on finding the optimal W's in every iteration, instead we just do one update step of 1+1 ES. This method is much more fast. It can handle much larger K values rather efficiently. And furthermore, and perhaps more importantly, this 1+1 ES update mechanism step that we propose does not require explicit probability density measurements. So it's very different from the log likelihood algorithm in that sense. So it updates the probability, these weights, the W values, based on the expected or the empirically measured average fitness of the corresponding solutions drawn from the corresponding probabilistic model. So it uses that, the average fitness, instead of the probability density estimates. And as a result, this particular 1+1 ES algorithm is highly compatible with GenAI and LLMs. So you can hook up a generative AI like a variation autoencoder or a GAN with as your underlying probabilistic model if you're working with this scalable TREO method instead of our previous 2018 method. Okay, so one more method I'll talk about. So we don't have to limit ourselves to generative models. There are also ways of using discriminative models. So this is a different kind of approach. We are talking about transfer stacking of surrogate models now. So in the previous case, we are talking about probability distributions in the X space, in your solution space. In a discriminative model, your model is not generating different X values. What your discriminative model is doing is, given an X, it's predicting Y or predicting f of X. So it's predicting the performance f of X corresponding to a solution X. It's not a generative model that allows you to sample a bunch of X. So this is the difference between the discriminative approach in this slide and the probabilistic generative approach that we were talking about earlier. So now again, think about this problem that you're solving on the left-hand side. There is some target objective function that you're trying to optimize over some subspace X. And this FT is expensive. As we said earlier, each evaluation can take hours or many dollars. Uh, so what you do is you try to come up with a cheap surrogate model. So this is an approximate model, f hat X, that is hopefully representative of FTX. Okay, so you want to find f hat tx, which is hopefully representative of FTX, which is your expensive function. But f hat is cheap because it's a surrogate model. It's a data-driven surrogate model. So you don't have to actually go and do a computer simulation or a physical experimentation. So once f hat x is accurate enough, it's a sufficiently accurate approximation of f of x, then you can optimize this fellow on the right hand side instead of the expensive guy on the left hand side. So that's essentially the idea. And what we showed is now the priors are in the form of these surrogate models. So these prior source data gives rise to source surrogate models. So these are models which map X to f of X, or the performance metric. It's not probabilistic source models anymore. Uh, but at the end of the day, in order to learn this f hat X, you are still building a kind of mixture model. So this is again very similar looking to the underlying framework that we proposed in the previous slides. But the only difference is that these Fs here that you see are not probabilistic generative models, but they are discriminative models, they're surrogate models. And we try to find an aggregation of the surrogate models that will give us an accurate f hat x. Okay, so that's essentially the idea. The rest of the framework is conceptually very similar. So I have all the sources that have given me a bunch of surrogates, and I have to aggregate them in some way. So I need to I have to write an algorithm that allows me to find the W's. The W's again play a similar role. They tell you the weightage of the corresponding source and the weightage of the target. WT is the weightage of the target. Intermediate target. Note, this is a f prime, f hat prime t is an intermediate target, and you combine it with the sources to get the final target model. Okay. And we showed in this paper, this is a 2019 work with discriminative transfer models, where it essentially is a rather simple proof to do, but under the assumption that all of these surrogate models have uncorrelated errors, uncorrelated with respect to the underlying target function. So if I assume that all of these source models have uncorrelated errors on the target function, then the optimal weights, so these optimal W's, are essentially just the inverse of the squared error. And this makes a lot of intuitive sense. So if you have large square error, if corresponding to a particular source model, you have a large squared error, then you want the corresponding weight to be small, right? So the weights are inversely proportional to the errors, which makes perfect sense. So we showed it in this 2019 TVC paper. This is Transactions in Evolutionary Computation. And we showed that this discriminative model-based transfer approach also leads to substantial speedups in performance given expensive optimization problems. Okay, with that quick overview of algorithms, let me now move on to some results, some benchmarking and real-world examples. So here's a paper that a preprint, I shouldn't call it paper, it's still not accepted anywhere. This paper talks about all of these benchmarks that I'm going to present now, and all the source codes are available. So feel free to download, use, read the preprint. Okay, let's get started. So here are the basic problem statements. So we take the benchmarks and we divide it into three categories. If you look at the names of the categories, this is all transfer optimization benchmarks that we proposed. It looks very similar to the 3 V's of big data, because we think of transfer optimization in sort of a similar way. So in big data, you have a huge amounts of data and you're trying to figure out ways of processing that efficiently. In transfer optimization, you can have huge amounts of source problems you solved, and you're figuring out efficient ways of using those sources, solve your target problem efficiently. So there is certainly a lot of connections there, and that's why we have this categorization. So we have big volume of sources, which is simply a large number of sources. You can have thousands of source problems you've solved before and priors drawn from those sources. Big variety refers to heterogeneity. So some of the sources might have different features from the target. The design space might not be the same. So that's what big variety refers to. Big velocity means that you have a continuous stream of tasks coming in, a constant stream of tasks to be solved, optimization problems. And you want to solve them one. So sort of like dynamic, but it's a constant stream, dynamic optimization, but it's a constant.
Excuse me, sir. Gupta, sir.
The,
Yes, sir.
sorry.
Sorry to interrupt you, sir. This is Dr. Ila Sharma, one of the coordinator in this program. Your voice was not coming, so I interrupted you. Sorry, sir. Now you are audible.
Oh, okay. Yeah, thanks. Okay.
Okay, sir.
Can you hear me now?
Yes, sir. Now
Okay,
you are audible.
cool. Okay, so as I was saying, the knapsack problem is a classical combinatorial optimization problem. All the big volume problems that I have that we have proposed use the knapsack as the benchmark. Planar arm, this is a continuous optimization problem. You're trying to find angles. You can change the number of members, the number of elements in the arm, which makes the problem heterogeneous. So you might want to transfer information from a robot arm with 3 members to another robot arm with 5 members. So that makes the search space different. So it's a very simple way to set up this heterogeneous setting. And then finally, for the big velocity, where you have a constant stream of tasks, we look at problems in attacking deep reinforcement learning policies. So deep reinforcement learning policies for playing Atari games, what we want to do is change the pixels in the game slightly such that the policy is fooled. So fooled, by that we mean the action that the policy is prescribing changes under these minor modifications to the Atari game screen, to the image. Okay, so again, it's just a success or failure setup, the attack one example. So you either succeed in fooling the policy, so it changes its prescription, or you fail, so it doesn't change its prescription. Okay, so we'll compare a bunch of algorithms here. We'll compare the AMTA, which is our log likelihood stack density estimation based procedure. Um, can you hear me? Hello? Can I be heard?
Yes, sir.
Okay, I just, there was some other interruption. Anyways,
Yes, sir. Some interruption is there. Sometime voice is gone, but this time you are audible, sir.
okay, thanks.
Okay, sir.
Okay, so if you look at it, as the number of function evaluation increases, our two algorithms proposed do considerably better than a standard canonical GA. That's the pink curve. The blue curve that you see here is evolutionary, a very basic evolutionary knowledge transfer algorithm based on this idea of case injection, which is very similar to the case injected genetic algorithm of CIGAR, as they used to call it, if anyone remembers. It's also a transfer algorithm, but very simple. So if you look at it, our probabilistic model-based methods are vastly superior to the baseline in terms of the number of function evaluations. So if I compare performance over the number of function evaluations, then we are doing excellent. But if you now change your, and this is both the case if you have just a few sources, 4 sources, or 1,000 source tasks, the performance of our algorithms is much better. But if you change your perspective slightly and you look at the performance over wall clock time, so in terms of wall clock time, then the story is slightly different. In the multi to one, so in the small number of sources case, it's still true that our algorithms are much better than the baseline. But when you look at 1,000 sources and you're comparing against wall clock time, then the AMTEA method, which is based on stack density estimation or optimal mixture coefficients, that becomes extremely slow. Okay, so the performance it reaches in a given amount of time, so in seconds, is much lower than some of the other algorithms, including just a standard G. So you need to be very careful. On the other hand, the scalable TREO algorithm still, so this is the one which is coevolution based. It's sort of a compromise, doesn't try to optimize perfectly every time, but as a result is more scalable and hence is faster. It still gives you some performance improvement compared to the baseline algorithms. Okay, so you need to be careful when you use these methods. If your method, the cost of your method is dominated by the cost of the function evaluation, then the top row is more relevant for you. Then it makes sense for you to use AMTA or STREO because the cost of the internal cost of the algorithm, the internal complexity of the algorithm is overshadowed by the cost of your function evaluations. But if this is not the case, if your function evaluations are reasonably cheap, then you might need to consider. And in some cases, maybe just a canonical GA is better. Not in this particular example, here a scalable algorithm is still better, but there could be other cases where you need to be more careful. Okay, so here is a similar picture that you'll see. This is the big variety case. Again, multi to one, so 4 sources, or many to one, 1,000 sources. The purple curve that you see here is an algorithm called MSSTO. So this algorithm is not by us. It's by another team that essentially does a domain adaptation. So it does a transformation. It uses that M transformation function to map the source domain to the target domain. Whereas our algorithms, the AMTA or the STREO, they do not have any domain adaptation. Okay, so they assume a unified space. So if this space is not originally unified, you just pad it with additional variables. So it's a very naive way of handling heterogeneity. Whereas MSSTO is a much more concrete way of handling heterogeneity by learning a mapping function. So again, in this case, because this purple algorithm is learning your transformation, in the big variety case, it gives you a significant improvement in performance when you're measuring with respect to function evaluations. So given a particular number of function evaluations, the performance we are getting with MSSTO is significantly better. But then again, when you change your perspective and you're looking at it from the perspective of wall clock time, the story changes. Since this MSSTO algorithm involves a rather complicated transformation mechanism, its internal algorithmic complexity is high. Okay, so therefore its wall clock time, its performance in terms of wall clock time is rather poor. So if I look at 1,000 source cases, it's the worst algorithm because it's consuming a lot of time in trying to learn the transformations, the domain adaptations. Whereas just a simple canonical GA is almost the best here in both cases. Not in terms of function evaluations. In terms of function evaluations, MSSTO is better. So if we assume that the function evaluations is what is killing, is what is taking the most, consuming the most cost, then by all means use MSSTU. But if that is not the case, if your function evaluations are cheap, then you should not. You should be a little more careful. Okay, so here's a similar picture now. Again, big velocity of attacks deep when applied to deep RL policies. So notice by attack, what we mean is we are just changing 4 pixels in an image. So we are allowed to choose which 4 pixels we can change and by how much. And based on this change, our goal is to fool a policy. So that means there's a pre-trained policy, RL policy, and its prescribed action should change given this minor, not noticeable modification to the input image. Again, what you see is sort of similar. So in terms of the results, the story is the same. If you look at the AMTEA algorithm, which is the one which uses stack density estimation, the wall clock time is very huge. So it consumes a lot of time in trying to perfectly optimize the weight values, the mixture coefficient weights. On the other hand, our STREO algorithm is much faster. So the wall clock time is much lower because it compromises on trying to optimize the weight values every time. Again, the MSSTO, which is this, whatever color this is, lies here in this band because again, it's trying to learn these transformation functions, which map the source domain to the target, which is expensive to learn. So again, it's sort of the same picture. In terms of wall clock time, one algorithm may be better, but in terms of function evaluations, if you're measuring in terms of function evaluations, another algorithm will be better. So you need to take these things into account when you use transfer methods. So those were benchmarks. Here, I'd like to show a real world application of transfer. So this is the magnetic sifter example I was talking about earlier. So essentially what you have is, this is like a sieve, a magnetic sieve, and you're passing some mixture, background mixture of cells through it. So for example, you might want to separate tumor cells from blood. Okay, so you'll pump your blood through this sieve, and the magnetic field generated by this magnetic sifter will remove some of the tumor cells. So you want it to remove the tumor cells so that then later on you can analyze whether these tumor cells are cancerous or not. So that's sort of like the application. So you pump in a mixture of cells through the sieve, and the magnetic and fluid forces, through the magnetic and fluid forces, so it's a multiphysics phenomena, you want to separate out a particular desired cell type. So in this case, maybe a tumorous cell, and then analyze it later on. Okay, so this is a multi-objective problem. It's multi-objective in the sense that you want to minimize the capture of the cell type that you're not interested in, and you want to maximize the capture of the cell type you are interested in. So you want to maximize the remover of tumor cells, for instance, the capture of tumor cells. They have to be deposited on the sieve. And furthermore, you want to minimize the amount of material. So you want to build cheap magnetic sifters, of course. So that's the cost of fabricating this part. So this is a 3 objective problem: minimize the amount of capture of the unwanted cell types, maximize capture of the target cell type, and minimize costs. Okay, so in this case, the source problems that you have are again magnetic shifter design optimization problems, again under different background cell mixtures. So you have different magnetic shifters that you've designed in the past corresponding to different cell mixtures that you've encountered. And you want to design the target problem is to design a new magnetic shifter corresponding to a new background mixture of different cell types. Okay, so this is a very clear example where you have different designs you've proposed in the past for different but related problems, and you want to use that data to be able to solve a new problem more efficiently. So this example and this study was carried out in a very recent paper that is being just recently published in TVC Extremo. It comes with open source code. So if anybody wants to use the underlying algorithm is general. It's just a general transfer optimization algorithm. But one case study in that paper looks at this magnetic sister design problem. So you don't have to worry about this problem if you're not interested in it. But all the general source codes are come freely with this paper. So just to show you the results, under different target problems, we compare NSGA2, which is sort of the baseline multi-objective optimization algorithm, with Extremo 0T, as we call it, and Extremo. Extremo is the method we've proposed. So Extremo is a transfer method based on discriminative models. So it's the surrogate model-based approach. Extremo 0T, we showed that essentially it boils down to the Parigo algorithm. So Parigo is Pareto expensive global optimization. So this is a classic paper from 2006 by Joshua Knowles. So we showed that Extremo 0T, zero transfer, is essentially the Parigo, and just Extremo is Parigo enhanced with all the transfer of discriminative model mechanisms. And as you can see, the performance that we can achieve. So this is average hypervolume on the y-axis is substantially better than the baselines. So without transfer, you're not able to do anything. Of course, Parigo itself, because it uses discriminative models without transfer, is slightly better than NSGA, which does not use any models at all. It's purely based on crossover and mutation. So it's much slower. Parigo is better than that, but Extremo is even better. And it's even better by virtue of making use of all the informative priors from previous magnetic shifted design problems that it's seen. Okay, here's a quick glimpse of theoretical and applied research beyond my own collaborators and research group. So there's this team from in the US, Eric Scott, who's a very good friend, and Kenneth de Jong, who proved no free lunch theorems in the case of transfer optimization. So the first no free lunch theorems came out of that group in the USA and was published in FOGA, so Foundations of Genetic Algorithms Conference. This is a leading theoretical venue for GA research, fundamental theoretical research on genetic algorithms. So this came out a couple of years ago. Then this paper here, this dealt with multitask optimization of different kinds of vehicles. So you have so they were trying to optimize the aerodynamics of different kinds of vehicles, such as sedans, hatchbacks, pickup trucks, etc. So they formulated this as a multitask optimization problem. And of course, this is a very heterogeneous problem because all of these different car types are totally different. They have different features. So in order to be able to come up with this unified search space, they proposed this unification through the latent space of a 3D point cloud autoencoder. So it's a fantastic idea how they were able to take different kinds of cars and find this unified space through a 3D point cloud autoencoder so that they can do transfer in that latent space. So this is a fantastic work that came out of Honda Research EU in Europe, industrial oriented research. Then you have on the bottom left-hand side here, reinforcement learning policies across different robot arms. So these are robot arms which are actually tasked to do things in the real world. Of course, it was done in a simulated environment. This is the meta world environment in which these robot arms are given different things to do, pull a door and so on, window open, button press, door open, etc. So there are multiple tasks that are assigned, and you're essentially trying to learn all of these reinforcement learning policies, all these deep nets. So you're evolving the weights of these deep neural nets to be able to solve the corresponding tasks, and you're doing this simultaneously. So this was another fantastic example of a real application of evolutionary multitasking in, of course, in a simulated environment, but you can imagine translating this to the physical. Then you have this particular work here, this came out of Tecnalia in Spain. So this is again an industry-oriented research organization in Spain that did this showcase. Then finally on the right-hand side, you have a group from New Zealand. This is the Victoria University of Wellington, a group from there that showed how you can use evolutionary multitasking to learn different hyperheuristics. So these are hyperheuristics to solve scheduling problems. So in operations research, manufacturing and operations research. So there's a wide range of applications that people around the world are showing. So it's really a promising area. So for those of you who want a deeper dive into the potential applications, please, I strongly encourage you to read this paper that I wrote a couple of years ago, a half a dozen applications of evolutionary multitasking. So in this paper, we identified certain categories. So we placed all the applications that we found up to 2022. So it's slightly old, and parked them into 6 buckets. So we had applications of evolution multitasking in data science pipelines. So this could be, for example, learning an ensemble of models at the same time using evolutionary multitasking, right? So evolutionary multitasking as a way to speed up ensemble learning, machine learning. Then you had evolutionary multitasking for embodied intelligence. So here you're trying to evolve controllers of different robots with different morphologies. So you have different robots with different bodies, so to speak, and you're trying to evolve their controllers at the same time, again, with information transfer through multitasking. And you can do this efficiently if you're using the multitasking algorithms cleverly. Then you have multitasking and unmanned systems planning. So you might want to optimize tasks, path planning of different UAVs, for instance. So there are multiple UAVs in an environment and you want to do their path planning simultaneously. Complex design, we already showed an example with aerodynamics of cars, as well as biomedical micro device design. So these are all multitasking and transfer in design applications. EMT and manufacturing and operation research, as the folks at Wellington have done. Then you have EMT in software and services computing. So this was also another very interesting application where people looked at software testing and formulated that as a multitasking problem. So in a complicated piece of software, when you want to test it, you want to find inputs to this software, to this piece of code, complex piece of code, that sort of activates different branches in that code. So corresponding to every branch that you want to activate in that code, you need to find a different input. So this can be formulated as a multitasking problem. The problem of finding different inputs corresponding to different branches of the code at the same time. And here they showed that you're able to do this kind of software testing more efficiently with, or at least comparably with the best algorithms out there using EMT, which is evolutionary multitasking. Okay, so with that, I'll conclude. I guess I've run over time substantially. So just to a few closing words. Transfer and multitasking optimization, of course, and I don't need to say this because I'm, I'm deeply involved in this field of research, and it's really fascinating for me. So it has huge promise with a lot of potential to discover these high quality solutions that we are talking about efficiently in domains in science and engineering where evaluating solutions is actually very expensive. So even in this domain, and that's the real setting. When generating data is expensive, how do you get these algorithms to deliver concrete outcomes? Okay, you cannot wait for an evolutionary algorithm to sample and evaluate thousands of solutions. So how do you get over that? How do you work with little data and come up with innovative solutions? So this is really the place where transfer and multitask optimization is, in my view, set up to thrive in the years to come. And one particular research direction which is extremely exciting in this regard is what I spoke about earlier, how you can integrate transfer algorithms with these pre-trained LLMs and try to exploit the informative priors coming directly from the LLMs. So now instead of having to solve a bunch of thousands of source tasks in the past and just relying on the tasks that you have solved previously and their corresponding priors models, what you can do is prompt an LLM in a way that elicits this prior from an LLM, a pre-trained LLM. So this could very well be an LLM that is out there, open source, a Llama or a DeepSeek or a ChatGPT, whatever it is that you like. By prompting it, you are getting these priors from an LLM, and it is sort of makes a lot of sense because an LLM is essentially trained on the entire internet effectively. So there is a very good chance that it knows something about the problem that you're solving. Assuming your problem is not cutting edge scientific research beyond anything anybody has seen. If it's that, then maybe LLM cannot do much. But if it's a problem which is relatively common, there is a good chance the LLM knows something about that problem. So it can give you those priors. It can allow you to sample solutions which are relevant in this kind of setting. So this to me is a fascinating direction of taking transfer optimization forward in this modern era of generative AI and large language models. Now, for anybody who's interested in this field, even briefly, I strongly encourage you to have a look at these introductory books. These are very simple books. The text will be available on this website of mine. And all of these papers and so on come with source code. All of our papers, almost all of our papers come with source code, and they are available at these links. So this includes the Extremo paper, which was published this year, as well as AMTA and others. They are all available. If they are not available, please feel free to contact me, email me anytime, and I'll send you the links. Okay, here are the references that we've spoken about today. I'll close with that. Thank you.
Thank you, sir. Thank you so much. Participants, if you have any questions, you can write it in the chat box.
Shall I stop sharing? Or maybe not.
Yes, sir, you can stop so that you will be able to see the chat box if there is any question.
Yeah.
Sir, myself,
Should time.
Dr. Leela Sharma, sir. I am one of
Hi.
the coordinator here. Nanda sir is having his exam today at 5, so he just left.
Oh, I see.
Mid-semester examinations are going on, sir.
It's the same here. Even in IIT Goa, the mid-semester exams are on. My paper is on Friday. So
Oh,
I'm yet to set the paper.
okay.
I'll have to do that after this talk.
I just took my paper today only, sir. At 4:30 I came. It was.
Oh, I see. I see. Is there another talk scheduled after this?
Yes, sir. There is a talk.
I see. What time is it supposed to start? Maybe what we can do is you can share my email ID with everyone and we can I can answer them offline.
Definitely, sir. There is a one question I can found, sir. Then we can write you a mail, and they can share their questions also. And if they reach to us, then we will forward you to also. There is a question
Yeah.
from Keshav Kumar that how multitask optimization is different from multi-objective optimization.
Well, multi-objective optimization is a particular task, a given task, which has multiple conflicting criteria, multiple performance metrics that you're interested in. A multitask optimization, each task in a multitask optimization problem can itself be multi-objective. So I can have multiple multi-objective optimization tasks. So that should make it clear that a multitask optimization is by definition more general than multi-objective optimization. Particular task in multitask optimization could itself be a multi-objective optimization problem. Does that make sense? Okay, I'm just going to put my email ID here.
Yes, sir. That will be fine.
Yeah. So there is no notion of a Pareto frontier. So if I'm talking about multiple single objective optimization tasks, then there is no notion of a Pareto frontier in multitask optimization. I'm interested in solving each of those tasks to the best of my ability. I'm not looking for trade-offs. Okay. And furthermore, the solution spaces, search spaces corresponding to each task could be different in multitasking, as we discussed. So there could be either the simplest case where the solution spaces are common and overlapping, so the design variables are all the same corresponding to all the tasks. Or you could have a situation where the design spaces are different. And that is totally different from a setting that multi-objective optimization can handle. In multi-objective optimization, there is a single design space. And each point in that design space maps to a vector valued objective function. But in multitask optimization, there could be different design spaces with different features. Some of those features may be overlapping, some of them may not be overlapping. So it's a generalization of multi-objective optimization in my view. So each task in multitasking can itself be a multi-objective optimization problem. Okay. Does this probabilistic model hold good for monotonically increasing functions? Yes, a monotonically increasing function would be reasonably easy to handle. It's when you have multimodality where things become challenging. Which optimization is suitable for multiple objective functions? I guess the field of I suppose this Mr. Indu Bhushan Kumar might have been asking about multitasks and not multi-objective, because the field of multi-objective is very well established. There are a bunch of problems out there which inherently are multi-objective. So I'm looking for, right? So yeah, I think he said yes. Yeah, so multitask optimization. So a very nice example, which at least according to me, is the domain. There's this domain called multi-concept optimization in engineering design. So when I'm doing engineering design, in the preliminary design stage, we are actually interested in evaluating a bunch of different design concepts. We don't decide on a particular design concept right at the beginning. We have a bunch of different design concepts and we want to optimize or partially optimize each of these concepts and then later on decide which concept we want to choose. So this field of research is called multi-concept optimization. If you're interested, I encourage you to go take a look. And for multi-concept optimization, multitasking is brilliant. It allows you to evaluate all of these concepts as different tasks and evaluate and optimize them simultaneously. Okay. So that's in engineering, that's a very, very strong use case. Of course, beyond that, like I was saying, in those categories of problems that we've identified in my survey, you have examples in machine learning pipelines, for instance, where you're training an ensemble of machine learning models. For example, you're neuro-evolving an ensemble of neural nets, and you can do that simultaneously. So across the entire ensemble, you train all these models simultaneously using an evolutionary multitasking algorithm. So that gives you a lot of efficiency there. Embodied intelligence. So you want to train controllers for different kinds of robots with different morphologies. So these controllers could have some related information, because you may be interested in training different robots for the same task, but these robots have different bodies, different shapes. So again, there are some overlaps between these controllers in the knowledge that these controllers encode, but you want to be able to find an algorithm that leverages that shared knowledge. And evolutionary multitasking again allows you to do that. So if a particular configuration of the controller works well for a particular morphology, this may transfer to another similar morphology. And by solving all of these morphologies simultaneously, you can get substantial speedups in, again, it's a reinforcement learning problem, so you can get substantial speedups in policy optimization. So there's a huge variety of possible situations where multitasking works or is potentially useful. It's a very new field. So let me add to this. It's not something that is very well established, and applications are very well understood. It's a very new field. We are ourselves exploring applications beyond just speed up. So there are things that multitasking allows. So one thing am I talking too much? Do we have time? Maybe I can take these questions offline.
Sir, sir, we have time because we have next session we have shuffle and we have a lab and that lab is followed by me only. So you can take
Okay.
2-3 minutes, sir, if you wish.
Okay. So one thing I wanted to talk about, again, I'm probably skipping some of these questions, but those I'm skipping, please email me. So if you look at a single task evolutionary algorithm, then you have this thing called selection pressure. So I come up with a population of solutions, I evaluate them, and then I rank them, and then I just choose the ones which are fitter. So the survival of the fittest idea that evolutionary algorithms implement. Now, one of the complaints of one of the issues with evolution multitasking typically has been that this selection pressure is too strong, and as a result, you rarely come up. Although evolution as an idea is very creative, so just random crossovers and mutations can generate a lot of creative solutions. But when we impose this very strong selection pressure on top of the population, what happens is a lot of the creative solutions die out, because the creative solution may not necessarily be so fit. Immediately, a very new solution with a new combination of genetic material may not be very fit given the definition of your fitness function. So as a result, what happens, a lot of these creative solutions will die out. On the other hand, we've seen, and there are certain, this is not published yet, but there is some evidence that what multitasking allows is that there is not just a single selection pressure. Because I have multiple tasks, each task is applying a different selection pressure. So as a result, a solution, a randomly mutated or crossover solution, offspring solution, even though it may not be good for a particular task, it might suit a different task. In effect, what's happening is the selection pressure gets modulated, it gets reduced. I'm reducing the selection pressure through multitasking, which allows a bunch of very creative solutions to survive through the evolutionary process. So as a result, what we're seeing is, and like I said, that this is not published research yet. I think there's an archive article that was on this. It came out of NTU. I forget the title. I can put it up separately sometime. Which showed that they coupled a generative algorithm with a multifactorial evolutionary algorithm. And then it came up with very, very creative type of designs. And they explained it by saying that, hey, in a multifactorial setting, you have these different selection pressures, and a solution can survive under different selection pressures. So the selection pressure is not so strong or not so focused on just one task, which is typically the case in EC. There's only one task and there's a very focused, strong selection pressure. You're either good for that task or not. If you're not good, you die out. But in multitasking, there are multiple tasks that you can excel at. There is no one task. And hence, a lot of creative solutions survive. So this is a fantastic other direction, which is beyond speed up. It's about generating creative ideas, creative solutions that multitasking could potentially allow. So it's a very new field with a lot of opportunities. So please, if anyone has any ideas, we can discuss, because I don't certainly have all the answers. Okay, suggest the task to handle. If constraints are becoming more complex, how to overcome or input using meta-heuristic algorithms? Okay, these are very specific questions. How about these type of questions? I'll take them offline.
Yes, sir. I would also prefer, because we are running out of time. So
Okay, good. So let's end here.
yes, sir. Definitely, sir. Thank you so much.